Да, значит, да. Добрый день всем, коллеги. Большое спасибо за...
Good afternoon, and thank you very much for introducing me, Olga.
Я сегодня расскажу о, значит, совершенно там, ну вот недавно полученных...
Today I will be presenting the data that we recently acquired, and that give us an idea of the actual scale, the scale of changes in the Russian forests. The reason for this kind of research, the one that I'm presenting today, is the objective to obtain a reliable and trustworthy estimate of the Russian forests' carbon budget. We all know that Russian forests are a unique phenomenon. The shear scale, 1/5 of all forests of the world, the 25% share, and several properties that Russian forests have, certain unique properties, such as 80% of the forest area in Russia is the area of permafrost, or more than 40% of the forests of the area are large. These are very homogeneous forests, and they are without precedent. At the same time, the forests are under a lot of pressure. They are affected by various destructive factors, including fires, and I will discuss that today. But there are other factors as well, and we know not enough about the impact of those factors. Although Russian forests are a phenomenon of global importance, still, we know too little about them. We must have this knowledge. There is a greater need for better understanding of Russian forests since Russia joined the Paris Agreement on Climate. The Paris Agreement on Climate states clearly that one of the conditions of Russia's participation in the agreement is comprehensive and accurate estimation of Russian forests' carbon budget. And this declaration, this statement, that this is Russia's commitment to provide a comprehensive and accurate estimation of Russian forests as sinks. Well, in order to meet it, we must know more about forests. Why today our knowledge is insufficient? Because today we know little about these forests because they cover such a big area. And in the Soviet times, even though there was a better aligned system of forest research, still not all forests were studied fully. In the last decades, we kept losing our information about forests. The data became obsolete, and basic characteristics of the forests that were obtained through ground techniques is valid for 25 years, well, maybe slightly more. So it is urgent that we update our knowledge of the forests and the sequestering capabilities. So this factor of the Paris Agreement, the factor of our need to collect comprehensive information about the forest's carbon budget, necessitates action without delay. We have a project. The project is called the Space Research Observatory for Forest Carbon. And as part of this project, for 18 months, or slightly less than 18 months, we have started to gather results. Some of them are surprising, some unexpected. And today, we wanted to share with you some of our findings. There are different methods to estimate forest carbons, but the official technique that is used for forest assessment is based on forest accounting. We need to know the area, we need to know the growing stock volume, we need to know the species composition. But we also need other information like density, age, productivity, the site index, the biophysical characteristics, the disturbances. We need to have all this information in order to estimate the Russian forest carbon budget. We started with already available products. Some of them had to be improved and upgraded significantly in order to ensure better temporal homogeneity, in order to produce time series. I will explain what we did and what it is that we achieved. I will not dwell too long on the technology to save more time to discuss the factors that are affecting changes in the forests. But I must say that the results that we managed to get are based on the automatic techniques for data processing that were developed at our institute and that use archives, updated archives, and satellite images, satellite data. So those long-term archives and satellite imagery, there was a presentation by Evgeny Nikolaevich Lukian, who made a presentation on the shared center, shared data processing center at the main conference, sorry, and the results that we got are based to a large extent on MODIS with 200 meters resolution. It's a long time series. This product is called MOD09. They were additionally improved by our internal technologies. And I will say a couple of words about these products. Like I said, Model 9 was pre-processed to filter clouds and shadows, and in order to restore the time series, the time series were restored with a different resolution. For some objects or assets, they are restored with a resolution of a day. For other assets, we use a 1 month resolution. And this is a product from one such software. This is a seasonal cloud-free image for spring, summer, autumn, and winter. In winter, it's not just 2 months, by the way, it's more than 2 months. All other images are based on 2-month series. So we wanted to remove the clouds to the best of our ability and to get the message that would be free of clouds as much as possible. We also need to remove snow in spring and autumn. When we are producing the winter image, we are trying to leave as much snow as possible on the ground. We are just removing the clouds and the snow on the roofs or the crowns, the canopy. We also applied LAGMA. This is the locally adaptive global mapping algorithm. We designed it ourselves. I made a presentation about it before, so I will skip the theory now and I will turn immediately to the results. Dima, for some reason I can't share the slides anymore. Probably I pressed the wrong button. Okay, thanks. My apologies. Probably I shouldn't be using the mouse. And moving on to, and now the slide stopped moving. So I should use the mouse. Okay. So the products that are produced with these technologies are shown here. This is the land cover of Russia. It's a map. It contains 23 classes, and out of them, 8 are forest classes. And there are 3 classes of tundra vegetation, 2 classes of bogs and marshes, and then there are other classes with a plant cover and without vegetation. Over here, for instance, you see a lot of burnt areas, and there is a special technique that we designed in order to detect deforested, unwooded, burnt areas. I will not talk about this today because there will be again a different presentation at a different breakout session within the framework of this conference. So here is this product. We update it every year from 2000 until 2019, and we had to work real hard in order to improve the stability of the classification and in order to improve this differentiation ability of the properties that we use of the indicators, and to train the system in such a way as to bring to the minimum the classification errors and to improve our ability to analyze time series. Again, a lot of work has been done. Has been made. I'm sorry. A lot of work has been done in the last year. This is the forest species map. I'm sure you are familiar with it already. It is different from the maps that I displayed before because it only classifies forests, and we have 12 different classes of forests here that are different in terms of dominant species. And again, a lot of time and effort went into producing this map. We significantly upgraded our maps of growing stock volume, and now we have time series for growing stock volume as well. Until now, we haven't managed, we haven't tried to attempt the carbon and to assess the dynamics of reserves. Some things were hidden from us. So when we first approached the analysis, we realized that in order to ensure homogeneous time series of growing stock volume, for instance, we had to do a lot of additional normalization of the original data from Moody's, especially for winter periods. And we had to produce fine-tuned adjustments of the calibration function to adjust brightness, reflectance, in order to estimate growing stock volume and in order to produce better filtering and the training, to improve the training samples. So we are only just now coming to an end of this big effort, and this is the most recent product of our making. And then there are other products as well that describe the impact of the destructive factors on the forests. For instance, here you see a product that describes the impact of fires, and it's just the area with fire, but behind every pixel there is a disturbance, there is some damage that describes the defoliation and deformation of the crowns of the trees, which are then recalculated into some integral index that characterizes the forest damage on a continuous scale. And then we can split these damages into classes. To align this map better with the conventions of the forestry industry, the maps that the legends that they are used to operate with. This is forest defoliation as a result of not fires, but rather of as a result of biogenic factors like pests. So everything that's not fire is shown on this map. And over here, you can see those bright red areas. That means severe damage. We know that dark needle leaf forests degrade very much and very fast. And those are mostly needle leaf forests. Now, we can take all these products to understand better the dynamics of changes in the forests. And if you match them, there are some very curious things that emerge if you look at the official statistics of forest area and the data from satellites. You will see that in general, the forest area numbers are quite similar. 781 million hectares, that's satellite data, and this is data from 2017, and 797, slightly more, but pretty close, according to Rosstat, the Russian Statistics Committee. There is a difference, but it's not very big. However, if you look at the geographic distribution of this difference, you will see that there is a territory, an area where official statistics underestimate the area compared to the actual data. There is a big difference in the Pskov region, for instance. We believe that this is because of the process of agricultural land being overgrown by forests. We will test this hypothesis later. And at the same time, we observe that there is a big underestimation, or rather, official data shows a much larger area in this part, in Yakutia, in the Baikal region, than the satellite data. Probably this is due to the fire effect and under accounting of the fire damage. we can perform additional analysis and identify forests outside of the official forest fund. We know that there are lands that are not supposed to have forests according to Russian registers. They're agricultural land, or they are forests, but they are forests on agricultural land. And we see that it is indeed the case. Here is this area where we have forests, but they are outside of the Russian Forest Fund, and they are associated with different kind of lands. And we see that outside of this forest fund, there are 34 million hectares of forests. And this gives you an idea, it's a good estimate or a proxy for agricultural land overgrown by forests, abandoned agricultural land. And this is a topic that is being discussed at different fora. And people are wondering what we should be doing with those forests. And in fact, there are different ways of obtaining those estimates. And our numbers agree to a large extent with the numbers that we find in literature. Let's take a look at the Russian forest area dynamics. This purple line, bluish line, shows the dynamics of forest area according to official statistics. There is a reduction, a slight reduction of about 160 hectares per year, but if you take a look at this curve, and this is satellite data, this is Earth observation data, there is a clear trend. The area covered by forests is shrinking. The trend is very strong. The rate is very high. And it is something rather unexpected. Our average estimate of multi-year rate of reduction exceeds 3 million hectares a year. And we believe it's a number that's worth paying attention to. This is much higher, it's a much higher number than any guesses, any projections that we could have made before computing this number. What could be the reasons for forest dieback, for forest disappearance in Russia? You can see here how much forest is damaged by fires. Two curves, one curve, a complete dieback area, and the bottom lower curve. Oh, no, the other way around, I'm sorry. This is complete curve, complete dieback, and this curve, the upper one, this one includes completely burnt and also highly damaged areas with a high probability of dying off in the near future. And these are the estimates, this is the data for the area that we collect in the year of the fire. That means we are not tracing the developments on the site in subsequent years. That information is not included into this model. For a long while, we have been producing models that would be seasonal or that would be dependent on species or the number of fires per season. And you can see at the the graphs. The black section here corresponds to the burnt area, and red corresponds to lost forest. And over here, you can see that we've got graphs between 2006 and 2015. Every plot corresponds to its year. There are two peaks on each graph, virtually, spring fires and summer fires. You will notice that in those peaks, in the spring fires, little forest is lost, while in the summer, when the fires reach their maximum, a lot of forest is lost. We assume, I'm sorry, I keep pressing the wrong buttons, I think. Okay, to go back to the slides, we assume that the seasonal variance is the main factor, and also the changes in the seasonal variance is the main factor contributing to the share of forests lost. My apologies.
Сколько я много уже говорю, да. Вот заканчивать. Быстро сейчас. Дальше. Еще. Вот повыше. Вот с этого, да. Ага. Так, все, спасибо. Вот. Ну и обращает на себя внимание, что относительное, значит...
So we notice that the average share of forest lost, the percentage is growing. Not only the area burnt is growing, but also the forest that will lose to the fire. That proportion is also rising. In 2006, about 40% of the burnt area resulted in lost forests. Now the share of forest loss exceeds 60%. That is to say, if an area is burned by the fire, the forest on the 60% of this area will die off. Just a second. No, it's not working.
Может быть, в навигаторе слайдов посмотреть.
Вот этими стрелочками. Все.
Oh, those arrows? Okay.
Вот. Ну, значит, на самом деле, еще одна цифра, которую я хотел...
And one other number that I wanted to voice today is that our estimates demonstrate that as of 2017, according to our estimates, about 89 million hectares are unforested. This is unforested burnt area surface. The fires happened in different years, but those areas are still not covered by forest in 2017. If you look at the dynamics of the accumulation of the fire area and the unforested burnt area, and at the same time, if you look at the curve of deforestation, you will see that they are two curves moving in the opposite directions, but they correlate very well. Now, let's consider the species structure, not just the area, but also the species. We know that some species are more or less stable, like larch or pine. Deciduous forests are even expanding their area, but you can see immediately that dark needle-leaf forests are losing their ground. Spruce and others come under the effect of various biogenic factors and also fires. the growing stock volume in Russia. Is it possible to understand the relative GSV per hectare? On this map, you can see more productive areas in the south of Siberia, another productive zone, and then a decline in the GSV as we proceed northward. Sergey Alexandrovich, only 3 minutes are left. Yes, thank you. There are still several important messages. When we analyze the GSV dynamics, we understood better the current increase or increment in the GSV. It's roughly 0.4 billion cubic meters a year, and this is important for us to understand. Before we had the GSV dynamics as such, we didn't know this number. We couldn't tell whether Russia was gaining or losing forests. If we know this, we will be able to say whether Russian forests are a source or a sink for carbon. Some say that they are a source of carbon emissions because there are many fires, because they are old, the forests are old. But we can confirm now with certainty that Russian forests are a carbon sink. They are a sink. And we can make our first estimates of the scale of the sink. If we were to remove all destructive factors and look at how forests change, if they haven't been damaged, if there were no disturbances, we will see another important figure. The undamaged forests continue to accumulate growing stock at a rate of 0.8 billion cubic meters a year. And this is the growth in the GSV, and it is per hectare, it is 1.7 cubic meters a year. And this is our current rate of growth. For decades, we have been saying that one piece of information that we missed is this current growth rate. Well, finally, with those numbers, with those inputs, we were able to calculate that figure. Thank you very much. And we received one question. Why this dynamic of 40 to 60% in the forest loss in the burnt areas? Well, I tried to explain this, or maybe I did not succeed well enough. Well, first thing that you need to understand is that there are changes in the seasonal burning, in the seasonal fires. There are more fires in summer now. I mean, relatively, not in absolute terms, relatively speaking, in terms of their shares. And there are fewer fires in spring. Burnt areas are mostly produced today in the summer, and that's why more forests die back in the summer. Why there is this change? Why there is this redistribution between the seasons? Well, this is a different question, and probably we should be analyzing climatic factors, anthropogenic or climatic factors.